All right, chemistry, let's start our video lecture for chapter 10, our combined section 1 and 2. We're going to focus mostly on, well, completely on section 2 here, talking about pressure. Okay. Now, you guys have some experience with pressure, but we're going to get very specific. We're going to get very strict with it here. So let's get started. First off, with regard to pressure, I want you to be able to define pressure and relate it to force. Then I want you to describe how pressure is measured. Yes, we still have to do conversions here. You're going to have to convert units of pressure. Then lastly, I want you to state the standard conditions of temperature and pressure. Here we go. Pressure and force. Pressure, which is represented by a capital P, is defined as the force per unit area on a surface. Gas pressure is caused by collisions of the gas molecules with each other and with surfaces with which they come into contact. Remember last lecture I asked you to picture gas in a bottle, the gas particles moving around the bottle, expanding, right, in their random, constant, rapid motion to fill that bottle. Again, picture those collisions again. The collisions of those gas particles on the container walls is exerting pressure, right? Any old collision is going to exert pressure, right? The collision with a car against a wall is going to exert pressure. It's going to exert a force. A baseball bat on a baseball is going to exert a force. And so are these gas particles on the container walls. This is pressure. It's gas pressure. The pressure exerted by a gas depends on the volume, the temperature, and the number of molecules present. So it depends on three things. So the greater the number of collisions of gas molecules, the higher the pressure will be, right? If it's the collisions that are exerting that pressure, then if we have more collisions, we'll have more pressure. How do we get more collisions? Well, we can make the volume smaller, right? We could have the volume be smaller so that as the gas particles move around that bottle, if the bottle's smaller, less volume, the gas particles aren't going to have to travel as far before they hit the container wall again. And so you're going to have more collisions, therefore more pressure. Or you can just increase the amount of gas in that bottle so there are more gas particles. More gas particles, more collisions, therefore more pressure. The SI unit for force is something that you probably haven't heard of before. It's called the Newton, capital N. And yes, that's named after Sir Isaac Newton. There's kind of this axiom that says one of the greatest honors you can receive as a scientist is to have your name remembered with a lowercase, right? So Newton, you become a unit of force, like Hertz or Watt or Volt, things like that, those lowercase names. But the SI unit for force is a Newton, capital N, and that is the force that will increase the speed, right? Increase, not just get it going. It has to increase the speed of a 1 kilogram mass by 1 meter per second each second the force is applied. And I know that sounds like a mouthful, and we're not going to do a whole bunch with the units here, but next year in physics you will. So it will be helpful to wrap your head around some of these ideas right now. But let's get an example. So consider a person with a mass of 51 kilograms. Okay, 51 kilograms. Don't worry about what that is in pounds, but it's a mass of 51 kilograms. At the Earth's surface, gravity has an acceleration of 9.8 meters per second squared. That means that there's going to be an increase in speed of 9.8 meters per second for every second that force is applied. That's why the seconds is squared on that denominator. The force that person exerts on the ground is therefore 51 kilograms multiplied by 9.8 meters per second squared. And we multiply those numbers there, the 51 multiplied by the 9.8, and we get about 500. But we're also multiplying the units. And so we're multiplying the kilograms by the meters per second squared. And that's where we get the unit Newton. Kilograms times meters divided by seconds squared. So pressure is a force per unit area. So the pressure of a 500 Newton person, okay, so remember that was a 51 kilogram person, right? So with a mass of 51 kilograms is going to exert 500 newtons on the Earth's surface. So a 500 Newton person on an area of the floor that is 325 centimeters squared, right? That's squared. Okay, that's a length squared, so that's going to be an area, and newtons were force. And we just said that pressure is a force per unit area. We're going to take our force, which was the 500 newtons, and we're going to divide it by the area, which here, in this example, is 325 centimeters squared. And so we come up with 1.5 newtons per centimeter squared. The greater the force on a given area, the greater the pressure. But also, the smaller the area on which that force acts, the greater the pressure. So we can make the pressure greater by either making the force greater or the area smaller. And we can think about this we might not have thought about ballet, but we can see this and we can imagine this. So here's our 51-gram ballerina here. There are a couple of different ways that a ballerina can stand that we're pretty familiar with, more or less. We can have our feet totally backwards, but we have the bottoms of 2 feet in contact with the ground. And so with both feet, the bottoms of both feet in contact with the ground, we're going to take up about 325 centimeters squared. And so that's our calculation from our example there. So we come up with 1.5 newtons per centimeter squared. But once that ballerina goes from that position up onto their tiptoes, but on both feet, right? Tiptoes on both feet, 2 feet in contact with the ground. The area in which this force, right? The force isn't changing. This human being is exerting 500 newtons of force no matter what. But it's distributed among a smaller area, 2 sets of tiptoes. Let's just say that's 13 centimeters squared. It's still 500 newtons. 500 newtons divided by 13 centimeters squared. All of a sudden we can see our pressure value is jumping up here. We're up to 38 newtons per centimeters cube squared. And now the ballerina is going to do something that's excruciating to look at, but go up onto 1 set of tiptoes. Right? The ballerina still has a force, exerting a force of 500 newtons, but now the area on which it is being exacted is halved. We're down to 6.5 centimeters squared. Still 500 newtons, smaller area, so our pressure is going to go up to 77 newtons per centimeter squared. Moving on to how we actually measure it. A barometer is a device used to measure atmospheric pressure, right? The pressure of the air outside. The first barometer was introduced by a guy named Torricelli. Okay, Torricelli. Maybe Torricelli. I'm not Italian. I apologize. But Torricelli. Let's go with Torricelli. In the early 1600s, Torricelli noticed that water pumps could raise water to a maximum height of about 34 feet. No matter what they would do, this water pump could raise the level of water to about 34 feet. And so he was wondering why this was so, and he thought that the height to which the water can be raised must depend somehow on the weight of the water compared to the weight of the air. And we're not going to get into why he thought that initially, but we're going to just move on from there.
Atmospheric pressure is the pressure caused by the weight of the atmosphere. Air pressure changes with altitude and can be measured with a mercury barometer. The height of the mercury in the tube indicates the atmospheric pressure in millimeters. If the atmospheric pressure increases, the air exerts more pressure on the mercury, causing it to rise in the glass tube. Thus, the mercury in the barometer rises with rising pressure. If the atmospheric pressure decreases, the pressure on the mercury also decreases. Some mercury will fall out of the tube and back into the container. Thus, the mercury in the barometer falls with falling pressure.
Thank you, Robot Lady. So, because of that idea of the liquid rising and falling, Torricelli reasoned that if the maximum height of a water column depended on its weight, then mercury, which is about 14 times as dense as water, could be only raised about 1/14 as high as water. So he tested his idea by sealing a long glass tube, which we just saw in the video of the barometer, at one end, and he filled it with mercury. He then inverted the tube into a dish of mercury, again, what we just saw on the last slide, and the mercury, in fact, rose only to a height of about 30 inches, which is 760 millimeters, which turns out is 1/14 of 34 feet. He was correct. So the common unit of pressure is millimeters of mercury, which is symbolized by mmHg. Also, you may hear this, and we'll probably do some conversions using these units. A pressure of 1 millimeter of mercury is also called 1 torr, in honor of Torricelli for his invention of the barometer. Again, that's one of those big honors to have your name remembered with a lowercase letter. So 1 torr is the same thing as 1 millimeter of mercury. Just remember that as we go forward. Pressures can also be measured in units of atmospheres. In fact, several equations that we use to do calculations about gases use atmospheres as the unit. Because the average atmospheric pressure at sea level, again, average, not all the time, it'll change from day to day, but on average, at 0 degrees Celsius, which is nice and cold, is 760 millimeters of mercury. Right? Because the average atmospheric pressure at sea level at 0 degrees Celsius is 760 millimeters of mercury, 1 atmosphere of pressure, which is abbreviated ATM, is defined as being exactly equivalent to 760 millimeters of mercury. And notice I wrote exactly in there so that 760, even though right now it looks like it's written with only 2 significant figures, it actually has infinite significant figures because of that word exactly. So don't let that throw you off when we're doing our calculations. In the SI system, the pressure is expressed in pascals. Right? Pascal is the name of another person. Again, big honor. Remember their name with a lowercase letter. 1 Pascal, which is abbreviated capital P lowercase a, is defined as the pressure exerted by a force of 1 Newton. Remember, Newton is a unit of force, acting on an area of 1 square meter. Right? 1 Newton over 1 square meter. That's the pressure of 1 Pascal. 1 Pascal, however, is a very small unit of pressure. It's actually very, very, very small. In fact, it's so small that for our purposes, it's very inconvenient. It's actually more convenient to express pressure in kilopascals, which we would abbreviate K, uppercase P, lowercase a, kPAs. 1 atmosphere of pressure, aka 760 millimeters of mercury, aka 760 torr, is equal to 101.325 kilopascals. This is a table that I want you to be aware of. Wrap your head around this information, see the connections. These are also going to be your statements of equality in here for your conversion factors, okay, that we're going to do, how about right now. So sample problem A. The average atmospheric pressure in Denver, Colorado is 0.830 atmospheres. We need to express this pressure in millimeters of mercury and kilopascals. So we're given atmospheric pressure in ATMs, in atmospheres. We want to get pressure in millimeters of mercury and then kilopascals. So my first setup, again, using conversion factors in the exact same way we have been. Now we're just talking about units of pressure, units of pressure, sorry. We're going to use the same factor label method of dimensional analysis. We're going to set up crosshairs. So for A, I'm wanting to go from atmospheres to millimeters of mercury. So I've been given atmospheres. I'm going to set up my crosshair. Remember, I'm multiplying here by a fraction that is equal to 1. 1 atmosphere is exactly equal to 760 millimeters of mercury. When I multiply this way, atmospheres will cancel. I'll have millimeters of mercury as my unit. Set up in the same idea, atmospheres multiplied by kilopascals over atmospheres. That way the atmospheres will cancel, and I'll be left with kilopascals. So again, set up your units first. Units first. Notice that I've set up my units first here. Did you guys notice that? Units first. Then go back and plug in my numbers. And so I will end with the numbers. Plug it into my calculator, and it turns into a simple plug and chug. All right, chemistry, that'll do it for this video lecture. I will see you next period.